Good morning, students. The topic of today's discussion is instruction formats. We already studied what an instruction is, what are the fields uh, present in
Yes,
the
ma'am.
instruction, right? What? Tell me, what are they?
Instructions, ma'am.
Hmm. Instruction
Memory
register.
reference,
Hmm.
memory reference, input output,
Hmm.
reference register,
Register
ma'am.
reference.
Regi- register reference.
Okay. Memory reference instruction. What are the components in that? What are the parts?
Opcode address mode bit.
Yes, very good. Very right. The most common fields found in an instruction format are operation code, address field, and mode field. Computers might have instructions of several different lengths. What we learned that what was the size of the instruction which we learned? What was the size of instruction? Yes, very good. 16 bits. 16 bits is not fixed. That size is not fixed. It varies. And the number of address fields in the instruction of a computer also depends on internal organization of its register. In this uh, topic, we are going to study about CPU organizations. Journal instruction has 16 bits, a generic one. Mode bit 1, opcode 3, address bits 12. So 12 plus 4 is equal to 16. Essentially, in this format, there is one address and there is one operation code. Further, it can be stated that the address can be, you can have two or more addresses. Here you have a single address. Instead of single address, you have address 1 and address 2. And on what this on what factor variation of these addresses and variation of the instruction uh, occurs, it is totally dependent on CPU organizations. How are CPU organized? CPU can be organized as a single accumulator organization wherein all the operations and computations are performed on the accumulator. You can have a journal register organization where R1, R2 journal registers can also be used for computations and operations. Um, Finally, you can also have a stack organization where you perform computation based on push and pop operation. These are the three types of CPU organizations. Please remember, this is very important. This is CPU organization. Right. So before understanding that, let us understand what is the meaning of example of accumulator type organization. In accumulator type organization, when you say add x, what does it implies? What does this implies? What do you mean by add x? Can anyone tell me, students? Please tell me what do you mean by add x? Expand this. In accumulator type of organization, which is the single accumulator organization, it is assumed that one operand is stored in the accumulator. Result would also go in the accumulator. Another operand can be found in the address specified by x in memory. If you expand this add x, it would become this AC equal to AC plus m of x. X is the address of the operand. One operand is assumed to be in the accumulator. Another operand is in the memory specified by address x. Add is the operation. This is single accumulator type organization in which you have got single address. This is single address. This is example for first type. Going ahead, you have got second type in which you have general register organization. In general register organization, you can specify uh, different registers, different number of registers based on the type of CPU organization. This one is taking three addresses. Add R1, R2, R3. R1, R2, R3 are three addresses. Okay, these are three addresses, and this means R1 is equal to R2 plus R3. In this general register organization, first category is A. A is having three addresses. B is having two addresses where the first address denotes the destination as well as the source for the first operand. So this you can write as R1 is equal to R1 plus R2. In this, only two addresses are specified. Okay. This is general register organization. Here, this is about moving the um, contents from one register to another register. Move symbolizes transfer operation. This transfer operation indicate that it can be R1 is equal to R2 depending on the particular computer and the format. Here it can be R1 equal to R2, or in this case R1 is the destination, or you can create a format in which R1 can be source. When R1 is source, it is like R2 equal to R1. When R1 is destination, you are transferring R2 contents into R1. When R1 is source, you are transferring contents of R1 into R2. This is with respect to transfer. In this example, there is an address of register and an address of memory. What does this indicate? It indicates that it is like adding the contents of R1 with the memory contents at x. This is R1 is equals to R1 plus M of x. Alright, this is also with respect to register organization. Register can also perform operations uh, and can store the intermediate results or the final results, and also you can perform operation on the contents of register and memory. The third one is stack organization. In this, you push an address on the top of the stack, and then you say add means it will pop the last two elements and perform the addition on those two, which we already looked at in our earlier example. That is stacked organization. This example we looked at, x is equals to a plus b into c plus d. So first you push a and you push b, and then you perform addition. Then you push c and d, then perform addition, because we are converting this into Polish notation, reverse Polish notation. And then you perform the multiplication of the result of a plus b and c plus d. So let us sum up what we studied so far. We learned three address instructions. Okay, in three address instructions, we have got one register and two memory addresses. Here also there is one register and two memory addresses. Here we have one memory address and two registers. Three address instruction implies that an instruction contains three addresses. Uh, the generic example which we saw, that apparently had single address. But now we are understanding how an instruction can have multiple addresses. So this is R1, A, B. This is our address part of instruction in which we have three addresses. This is three address instructions. You are performing addition of M of A and M of B and storing the result in R1. In the second statement, you are performing, okay, we are actually implementing this statement. So A plus B and storing in R1, C plus D and storing in R2, and then multiplying R1 and R2 and storing in uh, memory, M of X. This implementing this statement using three address instruction. This is like an example. How can you implement the same instruction or a statement using two address instruction? In this two address instruction, you have to first move A into R1, B into R1. No, add the contents of R1 with B. Means already R1 has A, so it is like R1 is equals to R1 plus M of B, which is equal to A plus B. Apparently R1 has got the contents of A because you are using move. Here you see move. You are moving A into R1, and then you are performing add. Add R1 is equal to R1 plus B. Later you are moving C into R2, and you are performing add uh, between C and D. C is stored in R2, so R2 and D. Finally, you are performing multiplication on the contents of R1 and R2 and storing that contents, that product, storing the product into memory X, denoted by X. It is like M of X. X is the address. This is two address instructions. All right, students. Uh,
Yes, ma'am.
Now you do for one address instruction. How can you do for one address instruction? One address instruction means it is the same statement. Can you do for single address? Yes, students. Single one address instruction. This is third type. In one address instruction, how is one address instruction? It will be like this. This is single address instruction. So in single address instruction, first you have to load A into AC. Look at here. This is our single address instruction. This is single address instruction. You see here there is only one address. This A is the address. Here A, B, T, X denotes memory addresses. You have RAM. In RAM you have memory address that is denoted by these symbols A, B, T, C, D, T, X. Load A. Load A means implicitly it is loaded in accumulator because single address instruction or one address instruction use accumulator implicitly for all data manipulations. Therefore, you are copying A into AC, then add B. Add B means what? Add the contents of AC with the contents stored at address B in memory, which is expanded here. AC equal to AC plus M of B. Store T means whatever is there in accumulator that you are storing into memory address represented by T. Students, are you able to understand?
Yes,
Yes,
ma'am.
ma'am.
Okay, then what is load C? Tell me quickly. Load C means what?
Contents in memory address are stored in accumulator.
Very good. Add D means what do you mean by add D?
Contents in accumulator and memory address are stored in accumulator.
Add D means
Contents in accumulator and memory are added and then are stored in accumulator.
very good, very good. Multi means yes. MUL means multiply. Multiply T means
Multiply the contents of T and then stored with accumulator and then stored in the accumulator.
very good. Store X means
The final result stored in memory address.
from where?
Accumulator.
From
From
accumulator.
accumulator.
Very good. You understand one address instruction?
Yes, ma'am.
Yes, ma'am.
Can you differentiate between one address and two address? In this, you see there are two addresses. Here there are two addresses. After the operation, you find two addresses, and in three address instruction, after the operation, you find three addresses. These are three addresses. So you have got three address instruction, two address instruction, one address instruction. Can you tell me zero address instruction? It uses a stack. Already we covered this. Tell me how to do this statement you in stack. Okay, let me begin. I will begin. You just add up. First, uh, I have to say push. I say push A. All right. Then what I have to say in stack. In stack, how do we implement this? Students, we did know in last class stack or operation that 3 into 4 plus 3 plus 4 into 5 plus 6.
Yes, ma'am.
So what we did, first we pushed 3.
Yes, ma'am. First we push the operands, ma'am, one after the
Tell me,
other, and the
yeah,
result is popped.
tell me now in this, for this example, push A. A is operand.
Yes, ma'am.
Adding the event or initializing the event.
First A is pushed, ma'am.
Push A, then say next.
Then B is also pushed, ma'am.
Very good. Push B.
And addition operation is performed, and the result is
So
popped, ma'am.
um, addition operation is performed, right? Add. Then
And the result is popped, ma'am.
why result is popped?
Is coming out. The result is coming out, ma'am. So it is called pop, ma'am.
No, result will still be stored in stack only, because
Okay.
until it encounters this uh, end of statement, means end of line, it go on doing the same thing. Now next it has to push
We'll also push C, ma'am.
C, ma'am.
push C, then
D.
Push B.
push D, then
Add, ma'am.
Addition is performed,
add,
ma'am.
then finally in the end
Multiplication.
Multiplication.
multiplication. Push A, push B, then add. Add means now what happened? Whatever value these two variables have, those are added and pushed back again into the stack. Then push C and D. Now our stack will have, first stack will have A, then stack will have A, B, then when it encounters add means it pops A and B, it performs addition and store the result A plus B. Next push C, so on top of this, it pushes C. Here you have A plus B, here you have C. When it encounters D, it pushes D also, and then add. Add means now what it should do, it should pop last two elements which are C and D. So A plus B is already there. Now C plus D, it adds and then push the result back into the stack. Then mul means what? Now there are these two operands are there. It pops C plus B D, and it says C plus D into A plus B. Finally, and then it performs the operation and store in the stack. Again it push. Now there are no more operations to be performed. There are no more variables or operands. Therefore, you just pop the result and store it in uh, memory. X denotes memory address. So pop m of x. Pop x means it is like m of x is equals to whatever is there on the TOS is top of stack. So top of stack now contains this. Understand, student? Zero address instruction.
Yes, ma'am.
Yes, ma'am.
Okay. RISC instruction. RISC is reduced instruction set computer. Our Intel machines are these follow this architecture, RISC architecture. Somebody raised hand. Any doubt? All right, let us go ahead. In RISC type of CPU, RISC CPU type consists of load and store instructions that have one memory and one register addresses. And computational type instructions have three addresses. This is a specific example. RISC are Intel based machine architectures. So in this architecture, we have got load and store. These two instructions have got two addresses, one memory address, one address memory 1 and register 1. So totally 2, followed by computational type instructions means add, multiply. These are computational type of instructions. These instructions can have three addresses, and these three addresses specify processor registers like R1, R2, R3. Okay, processor registers. PR, processor register. PR, processor register. Let us consider the example of x is equals to a plus b into c plus d again. This example, how it is implemented in RISC type of CPU. There is loading m of a into R1. A means memory address, m of a means the contents at that address A that you are copying into R1, transferring. You are transferring the contents of m of a into R1, and then you are transferring the contents of m of b into R2 and c into R3, d into R4. You perform all load operations. Four registers are loaded with A, B, C, D values. Subsequently, add operation is performed between A and B because A is in R1. Here, this is A. R2 has B. Result is stored back in R1. Now R1 has A plus B, which is R1 plus R2. Next add statement adds C and D. Add R3 is C. R uh, R3 and this should be R4. This should be R4. This is printing mistake. This should be R4. R4 has got D. So R3 is equals to C plus D. Here it is given. Look at here. By mistake it came as 2, but it is R4. So R3 equal to R3 plus R4. Now R3 has the addition result of C and D. Addition, both the additions are done. What is left? Multiplication is left. Multiplication is performed on the contents of R1 and R3. R1 has got A plus B, which is R1 plus R2. R3 has got C plus D, which is R3 plus R4, that you are multiplying and storing in R1, which is equal to R1 equal to R1 into R3. the result is in R1. Store operation would transfer the contents of R1 into X, which has got the result of this statement. Did you understand this?
Yes, ma'am.
Yes, ma'am.
Very good. That was all about processor, the instruction formats. This instruction formats. Students, don't get confused with the instruction formats topic which we studied in previous chapter and which we are studying now. This is in unit 4, that was in unit 3. If in unit 4 instruction formats are asked, you write about 3 address instruction, uh, single accumulator, general register stack, followed by 3 address, 2 address, and 1 address, 0 address. If it is asked in unit 3, then you write memory reference instruction, register reference instruction, and IO instruction. Because almost
Okay, ma'am.
the topic is similar, instruction formats. Heading is also similar. Therefore, you need to be very confident and sure whether you are writing answer for unit 3 or unit 4. Your exam question paper has got questions unit wise. Let us begin the topic of addressing modes. Addressing modes means what all addresses you can specify within an instruction. What all addresses we have specified so far, can anyone tell me? Within an instruction, what all addresses we have specified? Yes, students, in the address part, we learned that we can specify address directly.
Direct and indirect, ma'am.
We learned that we can specify direct address, we can specify indirect address. Likewise, you can have implicit address. For register reference, the implicit address is accumulator. So essentially, in this topic addressing modes, we are going to learn what addresses we can specify, in how many ways you can specify, and this addressing mode specifies a rule for interpreting or modifying the address field of the instruction before the operand is actually referenced. And this is quite important because it gives programming a versatility, so that a programmer can specify pointer to memory. A programmer can use indexing or just a counter or relocation. So different addresses would be required to perform different tasks. So it facilitates that, and it can reduce the number of bits in the addressing field of the instruction. If you know what all you can specify within a instruction. There are major 3 phases in an instruction cycle: fetch an instruction, decode the instruction, and execute the instruction. And there is a register called program counter that keeps track of the instruction in the program stored in memory that is to be executed next. PC holds the address of the instruction to be executed next. Okay, so it holds the instruction address of the instruction to be executed next, and it is incremented each time instruction is fetched. So when you fetch the memory, you increment the PC. All right, so this we already learned. And mode bit is also quite important because it specifies whether the address is direct, indirect, or it is any other format. Those all the formats we are going to study under this topic now. All the addressing modes specify the address in the address field of the instruction. However, there are two modes that does not specify any address, which are implied mode and immediate mode. These two are the modes in which address is not specified. Operands are specified implicitly in the definition of the instruction. If you say complement accumulator, what does it means? It means that it is implied mode because the operand is in accumulator. You don't have to specify the address or the operand. Here you just say complement accumulator. While studying register reference instructions, we learned that here you can say CMA, complement accumulator. When you say CMA, you are neither specifying the operand nor the address. Therefore, it is known as implied mode. The operand is in accumulator, and accumulator is uh, a default option in this case. So instruction format with mode field. In this mode field, you have a register. Here you get address, and if you remember this opcode, okay, here there is these two are reversed. First, here mode comes and here opcode comes in our earlier example. In this example, there is opcode, mode, and address. As I told you earlier, uh, whatever we are studying in generic format, uh, in various alternative formats, so that you should know that you can have in this way or in that way as well. So this is the instruction format with the mode field, opcode, and address. Zero address instruction in the stack organization computer are also implied mode. Since the operand are implied on the top of the stack, you are not specifying any address of the operands because the operands is on the top of the stack. So zero address is also under implied mode. Second one is immediate mode. In this mode, operand is specified in the instruction itself. In other words, immediate mode has an operand field rather than the address field. Can anyone give me an example of immediate mode? Yes, students, can anyone tell me? This is our instruction. In immediate mode, what all elements are there in this instruction? Yes, students. What did you understand immediate mode? In immediate mode, we have got operand value in the instruction, not the address. Okay, what is this? Can anyone tell me what is this? Here, what do you have? In MR instruction, what do you have here? In the first part? Are you all there, students? At least
Address,
this
ma'am.
called address. Here you have address. If you go to that address, what you will find? You will find the operand, right?
Yes, ma'am.
In immediate mode, operand value will be in the instruction. Here, suppose operand is 10. 10 will be directly placed in the instruction. Address will not be placed. Okay? Address will not be placed here. You place operand directly in the instruction field. This is immediate mode. In the first type of mode, here implied mode, there is no address, there is no operand. There is just the uh, operation. For example, CMA. That itself has the meaning that there is an operand stored in the accumulator. In the second case, there is a operand stored right in the instruction. Register mode. In this mode, operands are in registers. And the particular register is selected from the register field in the instruction. In the instruction, fields specify the register. A k bit field can specify 2 to the power of k registers. If there are 8 registers, then you should have 3-bit field in this instruction. If you specify 001, you are choosing R1 register. Understand? This is register mode. In register mode, instruction contains the register uh, bits that denote a particular register. Is it clear, students? In case you have doubt, please ask.
Ma'am, explain register mode once again, ma'am.
All right. In register mode, you have to specify the register name or number or address within the instruction. This is our instruction, right? In this, you have to specify in which register the operand reside. So how do you specify that? You have to have this in address. This is address part. In this address part, bits are used. K bit field is used to identify the register. If there are 3 registers, no, if there are 8 registers, you need 3 bits to identify each register. If there are 16 registers, you need 4 bits to identify each register. Consider that there are 8 registers, you need 3 bits to identify each register. So these 3 bits denote the register in which the operand is stored.
Okay, ma'am.
Understand?
Understood. Yes, ma'am.
R1, R2, R3, like that. How do you R0, R0, R1, R2? How do you refer R1? You refer R1 with 001 code. How do you refer
Yes, ma'am.
R2? 010 code. So that code will be available in the instruction.
Yes, ma'am.
Register indirect mode. In register indirect mode, instructions specify a register in the CPU whose contents give the address of the operand in memory. In register mode, if you go to R1, you will find the operand. Our operand is 10. Consider that our operand is 10. R1 contains 10 here, and R1 register is included in the instruction. In register indirect mode, there is this instruction. Here you have the register code. The register code is R1. R1 contains the address. Consider the address to be 800. There is a memory. In this memory, consider that 800 points to this location. Here you will find 10. This is register indirect mode. Is this clear? In register indirect mode,
Yes, ma'am.
register bits contain the register bit contains the address of the register. Within register, you have the address of the memory where the operand is stored. Auto increment or auto decrement mode. In auto increment or auto decrement mode, which is similar to register indirect mode, except that the register is incremented or decremented after or before its value is used to access memory. The configuration is same. This same configuration here also. This there is an instruction. In instruction, you specify the register bits. In register, uh, you have the address of the memory. In memory, you have the operand. Consider this 800. Here you have operand. After or before you access this value, this register contents are by default incremented or decremented. In increment mode, this 800 would become 801. In decrement mode, 800 would become 799. Automatically, after you access or before you access a value or the operand from the memory, this register contents are incremented or decremented. Is this clear?
Yes, ma'am.
All right. Now, that was all about uh, implied, immediate, register, indirect register, and auto increment and auto decrement, which dealt with registers. The address field of the instruction is used to obtain the operand from memory, right? In MR instruction, the address field specifies the address from which you obtain the operand. Sometimes what happens is you have to um, uh, obtain the address. You go to that address, you don't find the operand, rather you find another address, and when you jump to that location, you will find the operand. Sometimes there will be an address, you have to add some number to that address to obtain the operand. There are various ways in which address field can be used. To understand it further, you please try to understand what is an effective address. What is an effective address? Effective address is defined to be the memory address obtained from the computation by the given addressing mode, and effective address is the address of the operand. Uh, there might be an address which will not be effective address. You have to perform some computation on the address, stored address in the instruction to obtain the effective address. All right, that we are going to look at in our further addressing modes. Direct addressing mode, we know that here in instruction there is an address part, and this address part, contains the operand. If this address is 800, in memory it contains operand 800, means in 800 you have 10. This is direct address. Indirect address mode, how do you obtain the effective address? Effective address is equals to address part of the instruction plus content of CPU register. No, this applies to the next one. In indirect addressing mode, you have got the address which stores the address of the operand. This is address, consider it to be 800. And here when you go to 800, 800 you will find 500. When you go to 500, you will find the operand which is 10. This is indirect address mode. The following addressing modes are a little bit different. How to evaluate effective address is given here with in the form of this equation. To obtain effective address, you have to add the address part of the instruction. In instruction you have got address. That address part you have to add with the contents of CPU register. In CPU register you will have some value. You add this 800 with suppose in CPU if it is 100, you add both to get the effective address. Effective address is the address of the operand. Under this category you have got relative address mode, and you have got indexed addressing mode. You have got base register addressing mode. These three operate on the concept of having address part added with the content of CPU register. How it is done? Uh, I think we should continue this tomorrow along with the numerical example. There is this example. We will look at this example for all the addressing modes that we discussed. All right, students.
Okay, ma'am.
So,
Okay, ma'am.
so far is clear for all of you.
Yes, ma'am.
What? All of you. Okay, then, students. See you tomorrow.